Okay, welcome back, class. 5-2 is what we're looking at today. So you can just follow along in your note packet as I go through some of the problems. Today we're looking at the mean value theorem and Rolle's theorem. They are also existence theorem, just like the extreme value that we looked at last time. So we're going to be, it's a lot of similarities, but they allow us to do some different things. Okay, so what I'd like you to do now is take a few minutes and using this table, go ahead and plot the points onto that grid. And go ahead and hit pause on this video right now so that you have time to do that before I move on. Okay, so by the time you're done, you should get a nice little parabola. It looks like this. This little blurb talks about how in calculus, the derivative has many interpretations. One of the most important interpretations that it's a rate of change. And when speaking of rate of change, there are two rates of change that we have practiced this year. One is called the average rate of change, and the other one is instantaneous rate of change. Both are very important to our work in calculus. So let's look at the average rate of change first. Basically, that's slope between any 2 points. So it's your change in y value over your change in x value, which we have a formula for. So it is the f of b minus f of a all over b minus a, which is basically your change in y values over your change in x values, slope. So let's go ahead and take a look at this example right below. It says find the average rate of change of that function above from 2 to 12. So to do that, I would do the value at 12 subtract the value at 2 over 12 minus 2. Now let's go back up to the picture. We have the value at 12, the value at 2, and basically what it's asking you to do is to calculate the slope of the secant line that goes through that. Alright, so when we do that, we end up getting 3/10. Alright, now the other type of rate of change is the instantaneous rate of change. What is the slope at a very precise instant in time? And that is always the first derivative at a point. Now we've done some things where we approximated this using the average rate of change. We're going to do that again today. And we've done this where we have found the derivative of a function. We then plugged in the number that we want to test it at, and that gives us our slope. And we've also looked at the graph and tried to guesstimate what the slope is at a particular point. So up here, our example down here says, is the instantaneous rate of change at x equals 4 greater than the instantaneous rate of change at x equals 6? So we're going to look at the graph first, and then we'll show you a way that you can get a better idea of what's going on. So the slope at 4 is right here, and so that's the slope of this tangent line right there. And then we have the slope at 6, which is this tangent line right there. So does one look steeper than the other? And that's what it looks like. So right now we can say that 4 looks steeper. But we may want to prove it to ourselves a little bit. So we can estimate the slope at 4 is going to be about, and one of the ways that we talked about was using 2 points on either side and using that as an approximation of what's going on at the point. So for example, we can do f at 5 subtract f at 3. That's 2 points on either side. 5 minus 3. And so we get 2. The slope at 5, or the value at 5, sorry, the value at 5 is 9. And the value at 3 is 7. And so that gives us a slope of 1. So I don't know exactly what the slope at 4 is, but it's around 1. All right, now we can do the same thing for the slope at 6. So we pick a point just to the right and a point just to the left. We calculate that slope. So on the bottom is 2. The slope, or the value at 7 is, I can't read it, so I don't know. I guess we'll say 11. I probably should have used 8. Let's use 8. Okay. And the value at 5 was 9. And that's a 3. And so that becomes 2/3. So now you have proof that the slope at 4 is steeper. All right, so it says justify, so slope at x equals 4 is steeper. Therefore greater. Okay, that's probably good enough.